Welcome to this explainer. Today, we're diving into some fantastic concepts from Lecture 8 by Skip Uni. You know, programming can sometimes feel a bit intimidating, right? Like this giant, complex wall of text you just can't decipher. But today, we're totally stripping away that fear of coding. We're going to break down C++ data types using relatable, real-world analogies, taking you from familiar physical concepts all the way down to the microscopic, machine-level binary. By the end of this, you won't just know what data types are. You'll understand exactly how they live and breathe inside your computer's memory. Let's get into it.
Okay, let's take a quick look at our roadmap for today. We're going to cover 1. Containers and matter. 2. Primitive versus non-primitive types. 3. The core primitive types. 4. Memory, under the hood. 5. Calculating data ranges. And 6. We'll wrap up with the C++ coding challenge.
All right, starting things off with Section 1. Containers and matter.
So when we talk about coding, we talk a lot about variables. Think of a variable as a physical container, kind of like a backpack. You can put a laptop in it, or you can toss a notebook in there. The backpack is the variable because, well, it holds things. But C++ is what we call a statically typed language. It demands order, so we need strict rules for our containers. A data type is just the specific classification that defines exactly what kind of data you're allowed to put inside that container. You have to declare exactly what your container will hold before you can even use it.
And this is where coding beautifully mirrors the real world. In our physical reality, matter is categorized into different states, right? Solid, liquid, or gas. You absolutely wouldn't try to store a liquid in a cardboard box. The container has to match the matter. Similarly, in C++, data takes specific forms depending on whether you're storing whole numbers, precise decimals, or text characters. The data type simply tells the computer exactly what state of data it should expect to handle. Moving right along to Section 2, primitive versus non-primitive. Now that we've kind of bridged the physical and digital worlds, let's look at how C++ actually categorizes these data forms. It splits them into two major camps: primitive and non-primitive types. Primitive types are the built-in ones. They come predefined by C++, and because they're baked straight into the core language, they are lightning fast and manage memory incredibly efficiently. On the flip side, we have non-primitive types. These are user-defined and actually created by the programmer. We'll explore those advanced types much later in your coding journey. But for today, our absolute focus is on those fast, built-in primitive types.
Which brings us to Section 3, the core primitive types.
Let's look at the 5 fundamental building blocks of C++, and more importantly, exactly how much space they take up. For whole numbers without decimals, we use int, which takes up 4 bytes of memory. For basic decimals, we use float, which also takes 4 bytes. But if you need super high precision, double literally takes double the space at 8 bytes. For a single text symbol or letter, always in single quotes, you use a char, which is tiny, just 1 byte. And finally, bool, short for Boolean, stores simple true or false values, also using exactly 1 byte.
Now, a really crucial point here is understanding when to use which type, especially with decimals. A float is perfect for something like a basic percentage, say 98.30%. It reliably gives you about 6 to 7 digits of precision after the decimal point. But a double? That gives you up to 15 digits of precision. You'd use a double when you're dealing with highly precise mathematical experiments or complex scientific calculations where every fraction of a fraction absolutely matters.
Next up, Section 4. Memory, under the hood. Let's shift gears for a second and take a peek behind the curtain. We're traveling down from the high-level code U-type straight into the microscopic machine level. When you write code, the C++ compiler essentially acts as a highly efficient space manager. It looks at those predefined byte sizes we just talked about and uses them to carve out the absolute perfect amount of room in your computer's RAM. It doesn't guess, it allocates the exact space needed. And because computers don't understand English letters or base 10 numbers, that space is strictly used to store data that's been translated into machine binary, just zeros and ones. Let's actually walk through this translation process step by step, because it's pretty fascinating. Imagine you write the code char x equals a. Step 1, the compiler sees char and immediately reserves exactly 1 byte or 8 bits of memory. Step 2, the computer knows it can't store the literal letter A, so it looks up A in the standard ASCII table where a capital A has a numeric value of 65. Finally, in Step 3, the computer converts that 65 into pure binary, which is 01000001, and neatly packs those 8 zeros and 1s right into your 1-byte container. It's basically pure magic happening in milliseconds.
Now, contrast that tiny single byte with an integer.
If you write int roll number, the system instantly recognizes the int data type and automatically carves out a much larger block of 32 bits, which is 4 bytes. That space is now ready to store a much longer sequence of zeros and ones to represent a whole number.
Let's head into Section 5, Calculating Data Ranges.
So you might be wondering, why do these specific byte sizes actually matter so much? Well, they dictate the strict mathematical limitations of what a variable can hold. Let's anchor the math here with a very specific number, 256. We know a char container is 1 byte, which equals 8 bits. Think of each of those 8 bits as a tiny light switch that can only be flipped to 0 or 1. To figure out how many unique combinations of zeros and ones we can make, we calculate 2 to the power of 8. And 2 to the power of 8 equals exactly 256 total combinations.
And because we only have exactly 256 unique combinations in that 8-bit space, our char data type has a hard numerical limit. It can hold a range of values from exactly -128 up to +127, or, if we aren't using negative numbers, from 0 to 255. You literally cannot fit the number 300 into a 1-byte char container. There simply aren't enough bits. The physical memory directly dictates your digital limits.
Finally, Section 6, the C++ Coding Challenge.
To wrap this explainer up, I want to leave you with a quick, 2-part challenge to test what you've learned today. First, we know a char stores a single symbol, like the letter A. But what data type or concept would you use to store a full word or a name, like Varun? Think about how you might combine those single characters. Second, we just calculated that an 8-bit character has 256 combinations. Using that exact same logic, how would you calculate the massive limit of an integer? What exactly is 2 to the power of 32? Ponder these questions, do the math, and keep fueling that curiosity. Thanks for joining us for this explainer.
Welcome to Start Studying. Don't forget to like and subscribe.